All right, here we go. Second example, we're solving differential equations. We're going to separate and integrate. So let's read what example number 2 is asking us to do. Consider the differential equation given by this derivative formula. Find the particular solution, y equals f of x, given that f of 1 is equal to -4. Okay, so we're going to find the particular solution. Before we find the particular solution, we're going to find the general solution. So I'm going to designate, when we get to that point, I'm going to point out what's the difference. So what are we trying to do? We're trying to find an equation, the y equation, that when I take the derivative, it gives me this. Now, if you think about it, this is telling us there's a y equation that when you take the derivative, it equals x plus 1 over the original y equation. So notice that this derivative is in terms of the original y equation. Okay, so we're going to have to separate and integrate. So we're going to multiply both sides by dx. So multiply this side by dx, multiply this side by dx, and you're going to get dy equals x plus 1 over y dx. I have a mixture of x's and y's, so I'm going to multiply both sides by y. So now I'm going to have y dy equals x plus 1 dx. I have separated the variables. All my y's are on the left side, all my x's are on the right side. Now we're going to take the second step. The second step is integrate. So we separate the variables, and now we integrate both sides. So we're going to take the antiderivative. So the antiderivative of y, dy, would be y squared divided by 2 equals, the antiderivative of this would be x squared over 2 plus x plus c. Now, before I move on, I will say some students ask, well, wait a minute, you put a plus c when you took the antiderivative here. You didn't put a plus c when you took the antiderivative of the left side. You're right, I didn't write it down. Technically, there is one, and they're not necessarily the same constant. But, so I'll call this C1, and I'm going to call this C2. And if I subtract this constant to the other side, since they're not the same, they're not going to cancel out, but I'm going to get a new constant. So I'm going to skip this step of doing that and just say, I'm just going to write one constant, and I'm always going to keep it on the right side with the x's. This is the general solution. It's the general solution because I figured out my antiderivative, but I don't know what the c is, so it's just a general solution to my equation. Technically, I could, I guess, multiply everything by 2. If I multiply everybody by 2, I think you'll get this. And again, you might say, well, wait, if you multiply this by 2, you're going to get y squared. If you multiply this by 2, the 2's cancel. Then multiply this by 2, you get 2x. Multiply this by 2, shouldn't you get 2c? Well, I do, but if you double a constant, it's just going to be another constant. So I'm just going to label it c. So whether you write it like this or write it like this, that is the general solution. But we want a particular solution. And now I'm going to use what's called the initial condition to help me figure out what this c value is. Because they're giving me an x value and they're giving me a y value. So I'm going to plug them in here or here, doesn't matter where, and I'm going to figure out what that c value is. I'm actually going to plug it into the original one if you don't mind. So I'm going to take this and say y squared, so my y is -4. So -4 squared over 2 equals x squared, my x is 1 over 2, plus my x, which is 1, plus c. So now I'm going to use a little bit of algebra to solve for c. This is 16 divided by 2, that's 8. This is 1/2 plus 1 plus c. If you subtract the 1.5 this way and subtract 1.5 over here, you're going to be left with c. And whatever this is, which I believe is 6.5, is your c value. Let me erase this one. Since I use this version, this is the general solution. This is the particular solution. Plus, I believe that's 13/2. this is the particular solution. However, it's not in the form that they want. They want it as y equals some function of x. So we're going to use a little bit of algebra to move it around. But notice the difference. General solution, I still have the plus c because I haven't solved for the constant. Particular solution, I did solve for the constant using the initial condition, using the value, the initial, some people call it the initial value. Using the values that they gave me at the beginning, I'm able to plug in and solve for c in order to find that constant of integration. Okay, excuse me. So now let's solve for y. So I'm going to come over here. Since they want it as y equals something, so I'm going to multiply everybody by 2. And then I'm going to take the square root. However, remember, whenever you take a square root, you get a positive and a negative. And so this is kind of my solution. However, at this point, I got to remember the initial condition. Remember, the initial condition said when you plug in 1 into the x, your y should be negative. Well, the only way that's going to happen is if I only use the negative square root of whatever I got. And if you substitute a 1 in here and substitute a 1 in here, you should get what you're looking for. So if I plug in a 1 here, that's 1. Plug in a 1 here, that's 2. That's 3. Plus 3 is 16. The square root of 16 is 4. With a negative in the front, that's going to give me an output of -4, and I have my particular solution. The idea here is we're starting with a differential equation. We're going to separate the variables, all the y's on the left, all the x's on the right, and then we're going to take the integral, we're going to integrate, take the antiderivative of both sides. That's going to get us the general solution with the plus c. We're going to use the initial value, the initial condition given to us, in order to find a particular solution. And since they want the particular solution written as y equals something, I'm going to use a little bit of algebra to get to the y equals something. This is my final answer. So this is the function that when you take the derivative of this function, you're going to get x plus 1 over the original y. That's what we're looking for. All right, let's see. We'll do another one together in this video, and then we'll come back and we'll try one maybe a little bit more complex. So again, separate the separate the variables on example 3. Because we have a differential equation, we're going to find the particular solution through the point 2, 1. So let's multiply both sides by dx. When you do that, you're going to get dy equals 2xy dx. Oh, but now I have a mixture of x's and y's, so I'm going to divide both sides by y. And when I divide both sides by y, you know what? Let me do this in black ink. Dy equals 2xy dx. I should have only x's on the right, only y's on the left. So I'm going to divide both sides by y, and you get something like this. And now we're going to take the antiderivative. We're going to integrate both sides. Excuse me. Well, you might recall that in a previous video I said if there's a dy in the numerator, you can kind of push it off. So I'm going to push it to the side, leaving 1 dy. I'm doing that so that you can see it a little bit more clearly, that the antiderivative of this is going to be the natural log of the absolute value of y. The antiderivative of this would be x squared plus c. Great. This is my general solution. But I need to solve for y. I also need to solve for the c constant of integration. So let's do that first. So using the x and the y that were given here, let's substitute the y. So the natural log of 1 equals x, which is 2 squared plus c. And we're going to solve for c. All right. So this is 0. The natural log of 1 is 0. This is 4 plus c. So that means c has to equal -4. Great. I found this part. I can now go away from the general solution and put, this is the particular solution. So this is the particular solution we're looking for. However, it's not in this format, y equals something of a function of x. So I need to solve for x. I'm sorry, I need to solve for y and get the y by itself. So I need to get to the y, but it's inside of the natural log. So what do we say we do to undo a natural log? Well, we take an exponential of both sides. So we're going to take the exponential of the natural log of y equals the exponential of the other side. Oh, well, these are going to undo each other. So now I'm left with the absolute value of y. And then over here, I have an exponential to the e to the x minus 4. That's the same thing as e to the x squared over e to the fourth, if you want to do it that way. And then you could also leave it like this. And then we can say, well, I don't have the y by itself, I have absolute values. Remember, the absolute value of something equals an answer means that that answer could be positive or negative. And so to undo these absolute values, all I have to do is say plus or minus e to the x squared. You can either write like this, or plus or minus e to the x squared over e to the fourth. I guess it might be a little bit nicer to just leave it like this. Oh, wait, is it both plus or minus? Well, if I go back to my initial condition, my y is positive. Well, if it's positive, then it cannot be the negative version. So then this or this would be the answer. Can I test it? Sure. If I substitute 2 into my x value, because remember my x value is 2, 2 squared is 4, 4 minus 4 is 0, and e to the 0 is 1, and that's a positive 1. That's what my y is over here. So this or this, depending on how you want to write it out, is the solution, particular solution to this differential equation. We'll come back in the next video. We'll do some more separation and integration. What we're doing is we're solving differential equations. Solving differential equations means we're given the derivative function, the derivative equation. We're trying to find out the original function, but because my derivative is given in terms of x's and y's, I have to separate the variables. I have to integrate the variables. Integrate both sides, and then that's going to give us the original function using the initial condition to solve for that c, the constant of integration.